Hey, welcome guys. Yeah, so today let's talk about this one AA4 called egg drops with two eggs and n floor. And there's a generalization called the super egg drops. And also this problem is very famous. If you go to TED edX, there's a expression to talk about the animation talk about this problem in the two egg. Right? But the LeetCode has a hard version called super egg. So if you go to solution, there are so-called dynamic programming, and there's another third version which is using a mathematical way to solve it. And I think this is this section is a little bit hard to understand if you haven't seen it. So my video is just a rigorous proof everything in the pure mathematics, and we solve this in pure mathematical way. Okay, hope you guys subscribe to my channel. Okay, so let's start. So let me just talk about the problem. So let's solve the 2x use mathematics. So you're given two identical x, and you have access to a building with n floors labeled 1 to n. Okay, and you know there is a floor f. So this floor f, you know that if the x drop and floor higher than f will break, then any drop at or low below will not break. So basically, if you drop an egg which at a 10th floor, it break. So then it may break at the 9th or 8th floor. But if you drop at the 10, if you drop the egg at the 10th floor and it did not break, that means you go A or go any lower, any floor lower than 10 will not break. Okay. So each move you may take a so-called unbroken egg, and you drop it in from floor X. And if the egg breaks, then you will no longer use it. Okay. So and the goal is to, but you can, if it does not break, then you can reuse it. So return a minimum number of moves that you need to determine which certainty. Certainty means that you need to find the floor F such that it will not break. But if you go upper one floor, then it break. Okay. Yeah. So remember 100 is 14. Okay. So actually tell you that one optimal strategy is that drop the first egg and 9, and if breaks, we know that it must break in 0 and egg. Then you drop egg starting from one floor going up, so you get 10, 8. If the one floor do not break, then drop the first egg again at floor 22. It did not break. Okay, so you can check it 14. Okay, so let me just go into my PowerPoint and let's solve it 2x. Okay, so let's maybe solving the stupid case that that k equals to 1. So it's the number of eggs. So suppose you only have one eggs, right? And this guy is n floor. Then what else you can do, right? You need to start from the first floor, right? And if the first floor break, you know the number is, you know the tolerance is f0. If the first one do not break, you go to the second higher, and you go and you break, and you know the number is 1, right? So this is the only way, right? Because if because you cannot just go middle, right? If you just go middle and you throw out the egg and the egg breaks, then that means but then you do not know any answer, right? Because you only know that, oh, the possible answer is less than something. So this is not allowed. You must need to get the certainty of that floor. Okay. Yeah, actually, you can go to the TED video if you try to learn animation. But I hope you guys understand this question. Okay, so if you only had one x, right? So the answer will be n. Okay, so the answer f of n, let's say f of n will be n. Okay. How about you have two x? Okay, so suppose this floor is 10, right? 10. Let's say we do a trick. Let's say we start from the 4 and the 7 and the 9. Okay, so my strategy, so if you go just see the answer, the strategy is that you first throw one egg at the number 4 egg, the number 4 floor. If that eggs already break, right? Then you already spend one time for the first egg, and you can use the second. You have three floor you need to try, right? So the second egg need to try one by one, right? So the worst case is 1 plus 3, which is 4. Okay. So so there's a okay. So there's a situation. Okay, so the second situation is that your egg you throw egg into number 4 and it do not break. Then you go number 7 and you throw out and it break. That means you already spent twice. You already spent twice on your first egg, right? But if it do not break in 4 but break in 7, then you know the answer must be 5 or 6. So you need to use your first egg and throw a 5 or 6, right? So you at most still need 4. Okay. And if the number 4 do not break, number 7 do not break, but number 9 break, that means you already spent 3 times on your first egg, right? But you know the answer must add 8, then you still need 1 to solve it. So you get n equals 2. You still need 4. Okay, so that means if you're 10 floors, then at most you need 4 times. At most you need 4 times. So I hope you guys see the pattern. So what is the pattern? The pattern is that this is 1, right? And this is 2, this is 3, this is 4, right? So it's 1 plus 3 plus 4 equals to 10. Okay, so for k equals to 2x, we need to find how many times. Let's say the optimal. Let's say optimal is m times. Optimal is m times. Then you should start from your goal start from this, right? So 1, 2, 3, 4. So you need to find the 1 plus 2 plus 3 plus 4 up to m, right? Greater or equal to 4. Right? So the key is to find such m. Okay, so this is actually the solution for the 2x. Okay, so let's maybe do it, check it. So if n is 100, you can check m is 14, because 14 times 15 divided by 2 is 105, right? So you can check. And the optimal strategy looks like this, right? You go here. I mean, it doesn't need to be start from here is 1, right? You can start from this, right? Suppose so you're at 14, right? And 14 add 13 is just 27. And then you at 12 is right, so this need to be 13, right? And this need to be 12. So this guy is 39. Okay, so let's do some enumeration. So yeah, so this is my illustration. So suppose you draw your first egg here, and it broken, right? So you spend 1 time on the first egg because the first egg really suck, right? But you have 13, right? So at the worst case, that 1 plus 13 is 14, right? So the total you need 14. Okay. If the 14 do not drop, if you drop at 14, it do not break, then you go to 27, right? So you spend twice. You spend twice on your first egg, but you know the answer must be 15 to 26, right? So you know the answer must be 15 to 26, and the total has the 26 minus 15 plus 1, right? So 26, 5. Hopefully you see it's still 14, right? And you go to 37, so there's you go to 37 if 14 and 27 do not break, you go to 37, you throw a ball, which, oh, he breaks. That means you know the answer, you spend 3 times on your first egg, and you know the answer must be 39 minus 27 plus 1, which is still 14. Oh, sorry, this is 28. Because 37 is already, you check that it's not broken. 30. Yeah, so 30. Yeah, this is 11, right? Let's see. So this is sorry, so 14, 27. So this is 28, right? 28 and 39, right? So sorry, 38. I'm stupid because 39 you already checked that 38 is broken, right? So you need to check that 38 minus 28 plus 1, which is 14. And you keep going, right? So this is the answer. Okay, so if you're not sure my answer, you can solve this, right? By solving this, just you start from bound j equals 1, while bound less, and you add 1. So this is just the 1 plus 1, 1 plus 2 plus n. Okay, so you can check this, solve the solution. Okay, and you can also check that this is 100, the less is 14. Okay, and this is exactly follow the test video. Okay, so this is the 2-egg problem if you solve it. Okay. The problem is that what is 3 eggs? Okay, so let's go to the next problem. How many? Let's say we try to solve 3 eggs. But before we do this, let's try to write this more mathematically in 2 eggs. Okay, so within the 1x, then we get some function which called f of n, right? For 2x, let's say we need to find 1 plus 1 plus 3 up to n, right? Less than the floor n. So let's focus on this function. So this function is just n times n times 1 divided by 2. I hope you find it. But you can change it into the n minus 1 divided by 2 plus n, right? So which these guys n choose 2 and these guys n choose 1. Okay, so let me just write down. So n choose k is defined to be n factorial k factorial n minus k factorial. Okay. So actually, let's call it f1. Let's call it f2. Right. So f2 of n is n choose 2, n choose 1. So in 2x, what we are trying to do is that find such n, so such a small n, f2 of n greater than or equal to n. Okay. So for third x, we still do need to do the same thing, right? We still need to do the same thing. Okay, so before I do it, let's solve 3x. So once we solve 3x, then we will see a pattern. Then we can mathematical induction prove that nx is still correct. 3x. Okay, so now this problem is called a super x because you have 3x. Okay, who cares? Okay, so suppose you have 3x. Okay, then let's do this. Right? Suppose this guy is very high, and suppose I know the answer must be. Let's say I know the answer must be n. So suppose I know that the optimal solution in the 3x need to be n times. Okay, and so what is the let's see. So what is the first floor that I should put my egg? Okay, so suppose I put some I drop an egg where it break. Then let's suppose this k, right? So this guy is called k. Sorry, this guy is called maybe u. Okay. So in this I still have u minus 1 floor, right? So but I only had two eggs. I only had 2 eggs, right? So but I only have 2 eggs, right? So the optimal way, the optimal problem, the optimal number. So I can only okay. So let me. So I can only use. So I can only I only have n minus times to use 2x. To use 2x to determine the u minus 1 floor. Okay, so it means that the optimal solution is that the u minus 1 need to be equals to f2 n minus 1, right? This is just what we have proved. Okay. Okay, so that means u is 1 plus f2 n minus 1, right? How about so we solve this we know that u should be this guy, right? And now you see a trick. Suppose that I drop an x and the u and this floor do not broken. Then I should go to the next. So let's call it this is u1. Let's call these guys u2, right? So for u2, I already spend for u2, right? I already spent 2. I already spent 2 times, right? I already spent 2 times. I already spent 2 times to drop my so let's see. So this is u2, right? So for u2 I already spent twice on my first egg, right? So but you need to sum to n, right? So this length, right? This length is this length I can only use n minus 2 times to use 2x to determine the what? U2 minus determine the U2 minus 1 minus U1 plus 1, right? Because this guy is U1 plus 1. And this is U2 minus 1. So U2 minus 1 minus U1. U2 minus 1 minus U1 plus 1 plus 1 is the number of floor in the middle, right? So this is, I only need to use N2 times to use 2x. But which tell you that the U2 minus U1 minus 1 is just is F2 minus 2, right? Because this is what we just proved optimally. Okay, so U2 is U1 plus 1 plus F2 minus 2, which is you put in it, right? So you get 2 plus F2 minus 1, F2 minus 2, right? So this is U2. Okay, so now you get the answer, right? Because U3 will be F2. So do the same thing, right? Because U3 already spent 3 times, and the middle need to use the N minus 3, right? So you get the, so now you get the, you see your U1 is 1 plus F2 minus 1. U2 is F2 minus 1, F plus of F2 minus 2 plus 2, right? So U3 will be F2 minus 1, minus 3, minus 2, minus 3, right? Plus 1 plus 1 plus 1, right? So you get 3. Okay. Okay, so I hopefully you will find the answer, right? So you need to so what is the answer? So the answer is that you need to use the optimal floor, right? In the 3x, suppose the total number of n. You need to find such n that this this relation success, right? So you are trying to find n such that f2, let's say n minus k, right? From k from 1 to what? To something that we finish with, let's see, so plus k. Let's say, sorry, this is, let's say this is optimal to m, right? Need to be greater or equal to, need to be greater or equal to this large n. Okay, so right, but okay, yeah. Okay, so you need to do okay, but remember that you only use n, right? This is the optimal. You only need n. You only can use n times. So if you keep going, let's see. If you keep going, at some highest floor, right? This is highest floor that you can almost use your first egg, right? So in that case, that if you so you already spend n minus 1 time. You already spend your, let's see. Let me just move this. So you already spend your let's say you have this floor, right? And this is the sum floor, which is here, and then you already spend n minus 1 time. You already spend n minus 1 floor to drop your first egg. To drop your first egg, right? And all of it do not broken. Okay. So this is the only, so now you drop the final x. If this x broken, you know the answer must be this. If this you drop this x, it do not broken, then the answer must be the final one, right? So I mean this is the, so the remaining guy here can only be one. Can only be one, right? So that means this m, right, need to be n, right? Okay, so this is this guy must be n. Okay, so let me just write clearly. So we just mathematical proof that in the in the 2, 3x, right? This is our answer. So let's call it f3 of this is k, and this is so this is f3 of n. Okay, so let's try to model this. Let's try to solve this analytically. Okay, remember that f2 of s, right? We just proved it's basically s choose 2, right? S choose 1, right? So you can do it. You get so let's change some notation. Let's change this guy, change k from, let's maybe, so you see, this is yeah, let's maybe write this. So this is minus k choose 2, minus k choose 1, right? This plus n is greater or equal to n. So let's change the notation. Let's change let's flip. Let's change n minus k into maybe s or something. N minus k into maybe some other. Let's say it's maybe n minus k equals to v. Okay, so once you do this, then this problem become so when k equals to 1, v is n minus 1, right? When k equals to n, v is 0, right? Yeah, I mean, this is, yeah, okay, so let's do this. So you get v choose 2, v choose 1, right? So when k equals to 1, that is a minus 1, right? So n minus 1, and or start from v is 0. Right? Actually, v is 0, who cares, right? If v is 0, then 0 choose 1, 0. Okay, so 0 choose 2 is 0, plus n, right? N still fixed. Okay, so this is the our that series. So let's do v equals 0 and minus 1, v choose 1, v minus 1, v choose 2. Okay, so there's a theorem that I will not prove. Well, I will prove maybe in the final minutes. But basically, this is a lemma that binomial coefficient satisfy a property that I think if you start from v to let's say you choose v to send this called box, right? So such that v start from 1. So if v less than box, then just define to 0. Up to maybe up to the minus 1. Then this guy become this guy become n box plus 1. Okay. Okay, so for example, let's see. Let's maybe choose box to be 2. Okay, so let's say which I want to compute 2 plus 3, 2 plus 4, 2. Okay, so this is 2, 1 plus 3 plus 6, which is 10, right? And then this is exactly as I say n, right? So you can go n minus 1, and then 2 added 3, right? So it's 5 choose 3, which is 5, 4, 6, 3 divided by 6, which is 10. Okay, so this is the lemma that we will use. Oh, by the way, yeah. So this guy, this can be written as what? Should be choose n, right? Choose 2. This guy is what? N choose 3. And the previous, this n is just n choose 1, right? So we just prove f of 3n is n choose 3, n choose 2, n choose 1. Okay. And the f of 2n is n choose 2, n choose 1. And the f of 1n is n, right? So n choose 1. So we tell you that your mathematical instinct that if you have kx, the answer should be find fkn, which is n choose k, n choose k minus 1, n choose k minus 2, n minus choose 1, right? Greater or equal to a. So this n is the answer. So actually, this is the LeetCode solution. If you try to input, you just try to implement this solution to find such n. Okay. So let me just go to the solution to make you believe that what I'm saying is indeed 100%. So if you go to the solution section for the mathematics, then you will see their final answer is that you find some t choose x, and such that you need to find such k. Now it's number of kx. You need to choose t choose k, t choose k minus 1 up to t choose 1. such that this problem solve. There's a technical small detail that you can, there's a zero term, right? But actually it's similar to our approach. Right, so the answer is that you choose choose x from 1 to k. Okay, so this is what I just proved. For k equals to 1 or 2 or 3. Okay, so but okay, and then you can use binary search, but this is not so important. Okay, so our final mission, our final goal is to prove. It's a rigorous proof that fkn is actually unchoose k. Unchoose k minus 1. Unchoose 1, right? Greater or equal to. Okay, so our goal is to use mathematical induction, right? So key mathematical induction. Okay, so you use mathematical induction. This should be okay. So mathematical induction that we just proved that k is 1 or 2 or 3. Success, right? So very happy we prove it. Okay, so let's suppose that this fk works for maybe let me choose a label. Let's say alpha. Okay, so let's say f alpha works. Okay, so we occur alpha plus 1, right? So alpha plus 1 is similar, right? So remember that what is our recursion? Suppose now you have alpha plus 1x, and you already know you already spend n times. The optimal is n times, right? Then now the first floor, this need to be used. Let's say the first floor is u1, right? So u1 minus 1 can only be used can only be used alpha x, right? Can only be used alpha x, right? So u1 minus 1, u1 is 1 plus f alpha, right? We just prove it, right? N minus 1, right? So the same reason is u2 is basically 2 plus f alpha n minus 1 and my f alpha n minus 2. Okay, so your answer still be summation f alpha minus k from 1 to n, such that plus k, which is the greater or equal to n, right? So this is f alpha 1 plus n, right? Okay, and then you do the same trick, right? So remember, so your fn minus k, change the notation. Let's change the notation from k to, let's say, so you're starting from k to 1 to n, right? But you change your notation, it become f alpha, let's say n minus k s or something. It's s, which you can start from s equals 0 and choose to be n minus 1, right? So this is just s equals 0 and minus 1. Remember, f alpha is just it's just what? It's just s, right? S1, S2 up to S alpha, right? This is what we just proved it. Okay, so plus the original n, right? So let's just original n, so just n choose 1, which is our f alpha plus 1n. Okay, and you use the recursion the lemma that we need to use, where v choose box, start from v to 1 to n minus 1 become n box plus 1. So this term give you s choose 2, s choose 3, s choose alpha. Sorry, nice. So this is n and n alpha choose 1, right? Plus n1. So this term put in here. So it's n choose 1, n choose 2, n choose 3, up to n choose alpha plus 1. This is f alpha plus 1n. Okay, so this rigorous proof that the super X solution. Okay, so final result is just that the super X solution for kx is to find n such that n choose 1, choose 2, and choose k greater or equal to n. So this I called it, this is just why I call it fk. Okay, so this is the proof. So you can start from 2x and you do some trick and you go to you can prove that the kx. Okay, so then finally, let me just prove the lemma. Okay, so I think the lemma we need to use is to, I think it's this one, right? So it's v box, v from 1 to n-1 will be box box plus 1. Okay, so still mathematical induction. I think induction on, I don't know, maybe, let's see. Maybe induction on V. Sorry, induction on N. I think induction on N is okay. Okay, so I think N is when N is 1. That let's see. Let's so your V star from 1, right? So actually you can change this to be V star to box, right? Because only if V less than box, then there's no way you can choose it. So it should be a -1 box. V choose box, right? So this is it's box choose box, box plus 1 choose box, to N -1 box. Okay, so yeah, so let's do the mathematical induction, right? So let's say when N equals to, so the smallest N should be box plus 1, right? So when N equals to box plus 1, the left hand side is just box, which is 1. And the right hand side is also the box plus 1, which is 1, right? Okay, so suppose N equals to box, choose alpha is correct. So we just show that what? Show that box plus box. What the hell? Why I use box? Box plus alpha -1 box equals to box plus 1 box plus alpha. Maybe somebody in the next time tell me to not use stupid notation. Okay, so we need to compute N equals to box plus 1, right? Alpha plus 1. So the term I add here will be box plus alpha box, right? So and the right hand, and in this term, I will add this. I will lead this term become box plus alpha plus 1 box plus 1, right? So the difference is that I need to show that this term is the same as this minus box plus alpha box plus 1. Right, so I need to show this. Hopefully this is easy. Okay, so let's change the notation. Let's say this is N, this is K. So what we are just trying to show is that N choose K, just N plus 1, K plus 1, plus I move this term to the left hand side, right? So this is N choose K plus 1. Right, so our final relation is that just try to prove choose K plus 1 is a -1 K N plus 1 K plus 1. Okay, so this should be trivial, right? This is a high school problem. Okay, so quickly prove it. So K factorial minus K factorial and K factorial K plus 1 factorial and minus K minus 1 factorial. So right hand side, left hand side, let's just prove. Let's just move. Let's see. So I want to move K factorial out and then move N minus K minus 1 factorial out and then move N factorial out. Right. So this term become minus K. And this term become K and right, you come here. So it's N factorial, K factorial, and minus K minus 1 factorial, and this is K and minus K, which is N, right? So which is N plus 1 factorial, K plus 1 factorial, because this K and this K plus 1, and then you can N minus K factorial. So it's just N plus 1, K plus 1. Okay, hope you guys like this video. Hope this video teach you something. I apologize for maybe my writing is not perfect. Maybe my thinking is a little bit fast or something not clear to you. So hope you guys like the channel and subscribe.